Hello everyone and welcome to our web workshop on electric discharge modeling using COMSOL Multiphysics. My name is Sergey. I'm a technical support specialist. In today's session, I'll try to walk you through the applications, features, and functionalities of this module. The presentation includes a live demonstration. Please feel free to type your questions in the chat window or at any time, or even interrupt me with the questions allowed. Just a heads up, I've been working in COMSOL for slightly more than 9 years, and I have spent the last 2 of them here in Sweden in the global support team. My major is radio physics, and I'm supporting our clients across the world in AC/DC, radio frequency, and wave optic simulation. My secondary areas of confidence are vibroacoustic, microelectromechanical systems, and plasma plus electric discharge branches of COMSOL. Apparently, the last point explains why I'm hosting this event. However, I must admit I'm not so acquainted with the theory or practical side of electric discharge stuff. That said, I may not have the right competence to reflect all your possible questions, specifically the more theoretical or the more advanced ones. If that's the case, I will try to write all your queries down, discuss with my colleagues afterward, and deliver you their comments. The Electric Discharge Module is a recently launched add-on to the COMSOL Multiphysics software platform, introduced in version 6.3. This brand new module is designed to model and analyze various electric discharge phenomena in gases, liquids, and solid dielectrics. Key applications include modeling electric discharge phenomena, modeling streamer, corona, dielectric barrier, and arc discharges. This module serves a wide range of industries, from consumer electronics to high voltage power systems. Electrical insulation is a critical aspect of power systems. Consider this typical power grid example. Electricity generated by wind turbines is transmitted through high voltage power lines to end users in factories. Insulation in such system faces both internal and external challenges. For example, in transformers, use of oil for insulation requires modeling discharge transport in liquids. In circuit breakers, accurate and efficient simulations of electrical arcs are crucial for designing reliable systems. In cables, for materials like cross-linked polyethylene, it's essential to model space charge distribution within the insulation, requiring simulations of charge transport in solids. The electric discharge model can also model other electrical components and systems. In the aerospace industry, the electrical insulation challenges are amplified due to extreme conditions, the wide range of gas pressures, and the use of advanced composite materials like electrical insulation design more complex. Experimentation in such environments can be expensive or impractical. In these situations, simulation can offer a cost-effective and reliable alternative. Electric discharges are at the core of these insulation challenges. Generally, discharge processes can be divided into 3 phases. Charging, that includes separation and accumulation of charge on different materials or surfaces. Discharging, different types of and forms of discharges that can occur during this phase, and after discharge effects, both direct and indirect effects of discharges that can impact the system. The electric discharge module simplifies the modeling of complex electric discharge processes. Let's explore some examples. Streamer discharges. We can simulate streamer breakdown by considering impact ionization, attachment, and recombination of charge carriers. These processes are pre-built, eliminating the need to input chemical reactions manually. Streamer discharges in liquids are also supported. Corona discharges self-consistently. You can simulate the ionization layer and resolve nanoscale dynamics, capturing multi-scale discharge behaviors. Surface charge dynamics. You can compute surface charge accumulation and relaxation at dielectric interfaces, accounting for feedback effects between surface charge and the electric field. Solid dielectrics. It contains a, the model contains a bipolar charge transport model that includes electron holes and trapped electrons and holes, enabling space charge and electric field calculations. Finally, electric arcs. You can analyze both stationary and transient arcs using a magnetohydrodynamic approach with the pre-validated models with experimental data included. The module's interface is consistent with other COMSOL interfaces. As far as I know, you're already familiar with COMSOL Multiphysics. Therefore, you'll find it easy to get started. The module includes diverse tools, among which the key ones are the electric discharge interface and the arc discharge multiphysics. They cover two main approaches to simulate discharges, via the transport drift diffusion equations and via the magnetohydrodynamic formulation. There are also some other tools included in the module, such as extra AC/DC, radio frequency, and chemistry-based interfaces. I'll try to introduce the main stuff within my presentation. When presenting the brand new electric discharge module, we can't help comparing it with the plasma module. The latter add-on has been existing in COMSOL for a while and used in the similar or related context. You may wonder about the differences between the electric discharge module and the plasma module. For gas discharges, the electric discharge module is designed for atmospheric and high pressure gas discharges, while the plasma module focuses on low pressure gas discharges. The electric discharge module includes features like photoionization, crucial for modeling atmospheric pressure discharges. Finally, the plasma module, on the other hand, is targeted for industrial plasma processes used in, for example, semiconductor manufacturing. In addition, the electric discharge module also includes simulations of discharge and charge transports in liquids and solids, unlike the plasma module, which is limited to plasma modeling in gases only. Even though a motivated engineer can definitely track down a lot of similarities between the main interfaces on these modules, let me highlight that the electric discharge interface is tailored towards power electronic simulations and offers a great user experience, as it allows to avoid any direct specification of chemistry behind the discharge. Conversely, the plasma interface requires this chemistry to be tediously clarified. Tediously clarified. Time to share technical details. The module's flagship physics interface, the electric discharge interface, integrates multiphysics capabilities such as built-in charge transport module coupled with electrostatic for various dielectrics and advanced numerical methods, including algorithmic formulation for transport equations. Application-wise, you might want to use this interface to simulate streamer or corona discharge breakdowns, as well as surface discharges across solid gas interfaces. The interface simulates atmospheric and high pressure discharges by solving transport equation for electrons, positive ions, and negative ions. It incorporates processes like impact ionization, attachment, and recombination. On this slide, you can find some crucial considerations that have to be considered when dealing with the gas discharge simulations. The electric discharge interface, like the plasma interface, relies on the fluid form approximation, which uses a single moment description based on continuity equations. This approximation is generally valid when the product of gas pressure and discharge gap length exceeds 0.1 or multiplies centimeter. If that product falls below 0.1, the fluid model becomes inaccurate and particle models are required. The fluid approximation remains valid for reduced electric fields up to 1500 townsends. The behavior of electric discharges differs significantly under varying pressure gap products. For atmospheric pressure discharges where that product exceeds 200, the local field approximation is commonly applied. The electric discharge interface is particularly focused on modeling such conditions as shown in the figure on that slide. An important sub-feature of the gas discharge capabilities is photoionization, which plays a critical role in positive electric discharges. In these cases, electrons move in the opposite direction to the discharge's propagation, requiring a mechanism to generate seed electrons. The built-in photoionization model is based on the radiative transfer method, enabling efficient computation of photoionization rates. The interface also supports modeling discharges in liquids, such as transformer oil. It solves transport equation for electrons, positive ions, and negative ions while incorporating key processes like field ionization, attachment, and recombination between these charge carriers. For solid dielectrics, the interface features a bipolar charge transport model to simulate materials such as polyethylene layers. The equations account for electrons, holes, trapped electrons, and trapped holes, and include phenomena like trapping, detrapping, and recombination. These enables accurate modeling of space charge dynamics inside solid dielectrics. The dielectric interface boundary feature automates the modeling of surface charge accumulation and relaxation at dielectric interfaces. It automatically sets up the governing equation, and users can include surface charge transfer due to surface conduction. The electrode boundary feature offers an unified interface for specifying boundary conditions for electrical potential and charge carriers. Users can define these conditions in a single settings window. Additional built-in features include discharge current variables for computing discharge current through electrodes, and the surface emission mechanism supporting secondary emission, field electron emission, and thermionic emission. The electric discharge module also includes a dedicated arc discharge interface, or rather multiphysics interface. It would be useful if we were to simulate dynamics of an arc discharge under the assumption that the initial channel have been heated up and the arcs have formed. Here we treat the system as a conductive fluid via the magnetohydrodynamics approach. That said, we're going to deal with the system under local thermal equilibrium conditions. This interface integrates three physics: magnetic and electric fields, heat transferring fluids, and laminar flow. It also features a set of built-in multiphysics coupling, such as magnetohydrodynamics coupling, electric equilibrium discharge heat source, and non-isothermal flow. In addition, the model provides application library models that have been verified against experimental data. This slide shows a screenshot of the arc discharge multiphysics interface. It combines ease of use with robust capabilities, allowing users to start modeling quickly and efficiently. For complex discharge chemistry, the reaction engineering interface allows users to specify customized reaction schemes. This interface can generate a space-dependent model, enabling seamless integration of custom chemistry into the simulation. Additionally, the charge carrier transport interface provides flexibility for customizing boundary conditions and transport equations. I believe the reasonable question here is where this approach should be selected. The possible yet super complicated example is the streamer to arc transition. Currently, we do not have any dedicated interface to model it within the electric discharge module. What you can do is to use the general chemistry-based interfaces to set up your own fully developed discharge chemistry coupled with the regular electrostatic, heat transfer, and CFD interfaces. The electric discharge module includes two comprehensive material libraries. The key one is called Electric Discharge Material Library and provides data for common gases, liquids, and solid dielectrics, enabling quick material selection without manual input and/or literature review. Another library called Equilibrium Discharge Material Library offers temperature-dependent properties for gases, including density, heat capacity, and thermal conductivity as functions of temperature. The latter is meant to be used together with the electric discharge, with arc discharge interface, sorry. The module supports connecting the electric discharge interface to the electrical circuit interface for physics circuit coupling. This allows users to simulate discharge processes driven by external circuits. Application library models demonstrate these capabilities, providing ready-to-use templates. And the model also employs advanced numerical methods, including logarithmic formulation, which solves for the logarithmic value of charge carrier densities, ensuring strictly positive results and capturing variations over several orders of magnitude. And streamlined diffusion stabilization that enhances accuracy and efficiency when solving transport equations. The screenshot illustrates how the solver captures significant variations in charge carrier densities while maintaining solver stability. Just to make it crystal clear, this mainly propagates to the electric discharge and the charge carrier transport interfaces. The initial condition for the carrier number density cannot be zero and is set to a finite small value by default. They had better represent some initial electron seed in a zone of interest to ensure fast convergence. Same is true for magnetic hydrodynamic simulations, providing initial non-trivial temperature and conductivity distributions. For transient electric discharge models, it is often beneficial to add an electrostatics initialization study step before the main time-dependent study, such that the transient study has good and consistent initial values. Electric discharges often exhibit multi-scale dynamics across both time, sub-nanoseconds to seconds, and space, micrometers to meters. These the module's adaptive meshing technology and automatic time stepping efficiently handle these variations. For example, in a negative corona discharge simulation, the solver dynamically adjusts time steps to capture nanosecond scale dynamics, reducing computational resources by more than 3 orders of magnitude compared to the fixed time stepping methods. The electric discharge model enables efficient analysis of discharge-induced effects, including lightning-induced voltage that can be used to compute the voltage generated by lightning strikes, and you can compute the voltage generated by lightning strikes and perform a transient full wave simulation. And multi-physics effects, where you can seamlessly integrate with other COMSOL products to study discharge-induced multi-physics phenomena. For instance, discharge-induced flows with the ionic wind applications in mind. Next, I'll show you some of the above-mentioned functionality with a live demo on simulation of double-headed streamer excited in parallel plate electrodes configuration. Initially, a cluster of electrons is positioned between two electrodes, spaced 1 centimeter apart, and subject to a 52 kilovolt voltage. Negative and positive streamers propagate toward the electrodes, exhibiting electric field and electron density consistent with the reference simulation results. So let me open COMSOL Multiphysics, or actually I have already had it opened. So let's build a pretty simple model. It will be a 2D axisymmetric model. We'll use the electric discharge physics and select the time dependent with initialization study. The modeling space is super simple, so we'll switch to centimeter length unit and create a simple rectangle, but I'm also gonna add a small layer like this. As you can realize, that's layer represent kind of track for streamers to propagate toward anode and cathode. And the reason we introduced it is to refine mesh within that track so we can capture the complex dynamics. But we'll return to that later. After we build geometry, let's add a material from the application libraries, and that's a good chance to me to demonstrate it. So the electric discharge material library, and I'm gonna select nitrogen. We can see that it has some data. Employed. There is also some missing data, but that's for negative ions. And that's something that we don't want to consider in this particular simulation. So don't worry, we'll switch one of the options in the physics interface and got rid of these stop signs. So the electric discharge interfaces help us to add any dielectric medium to our system, such as gas, liquid, or solid. We can select them all, and then you can see the 3 default nodes with the extra boundary or volumetric condition that can be added. But here we're gonna study only streamer discharge in gas medium, so we'll leave only gas medium. Here we can select the required charge carriers that will be electrons and positive ions, and that help us to get rid of that stop signs. For what it's worth, let me mention that we can also describe some of domains like pure insulator or conductor and do not consider charge transfer. That is true for any type of media. And that's, I would say, even more relevant when we have solids in our setup. But so, as you can see, we will consider diffusion. We gonna extract electron and positive ion mobility from material data and define diffusion coefficients via the Einstein relations. If necessary, we can define our own data. For example, to compare it with some published results or, I don't know, reference data. Let's keep all default settings. So, and what are we missing? We are missing electrodes, so let's add bottom grounded electrode and top electrode with 52 kilovolts. We can even create a parameter. And that's one of the cool small enhancement in the 6.3 release. What else? As I said, it's crucial to define a reasonable initial values for the simulation, and especially here when our problems made statement assumes that we have an initial electrode seed in the middle of our simulation domain, so close to the axis. So let me define such a distribution that should be a kind of smooth profile of electron density. I'm going to introduce that as an analytic function, and to save time, let me copy paste a long but now pretty easy expression, and I just plot it so you can understand what's going on. So here you go. That's a smooth concentration up to 10 power 14 with the background level of 10 in the 8th power. That's just a background non-ionized media. So let's call that N0 and specify as an initial electron density. We also should keep track of the positive ion density and its initial values, and now a good practice is to make them consistent. So at the time equal to 0, we have an electroneutral system. Okay, next step is meshing. As I said, our idea is to refine the mesh in the track by their axis. So our best bet is to use the mapped meshing with the settings like these. So it's obvious that density will be concentrated along the axis, so we refine our meshes toward it, and we're also add a pretty fine distribution in the vertical direction. The outskirts of our simulation domain can be meshed with the regular free triangular mesh. Okay, so let's define the output times for our simulation. We're gonna save a few time steps and run a simulation up to 2.5 nanoseconds. Before I launch the simulation, let's press that selected Show Default Plots option that help us to get some default plots, even though they're empty right now. I don't want to have any 3D revolution, so let's focus on the default 2D plot. My idea is to configure that plot and monitor it while solving. So that's what I've done. Let's even call it electron density. Charge density. Okay, and another cool consequence of launching study with the show default plot. That's now we have reconfigured solver configuration, and I would like to adjust that a bit. As you can see, by default it uses the adaptive time stepping, and that and the maximum and minimum steps are going to be defined based on tolerances and mesh parameters, but our idea is to limit the maximum time steps taken so that we won't skip any important dynamics of our streamer discharge. So that's, I'm gonna limit the maximum step to 1 in the power of -11. And so the last thing, that's to select our plot dedicated for tracking down results. So let's launch the simulation. Starting from the center, we can observe two streamers develop toward the electrodes. These streamers have different propagation mechanisms that result in different morphologies and propagation speeds. The top streamer is anode directed and develops a negative space charge density since the electric field pulls electrons ahead of a streamer. The bottom streamer is cathode directed, and the electrons are drifting in the opposite direction of the streamer propagation. The propagation of the cathode directed streamer is only possible because it is given a high enough background electron density. For simulating a positive streamer in a weak field, the photoionization effect has to be taken into account, and the electric discharge module features such a tool. So you can see that two streamers have started propagating, and their morphology is different. And in order to save time, let me cancel that simulation and instead bring a solved model up with you, so we can see the final distribution. We can also analyze the space charge density, and here we can clearly see from the beginning. So that's a negative streamer, that's a positive streamer. Watch out in the legend. Oh, we can also analyze the electric field along the axis, and we can see a sharp edges of positive and negative streamers. Finally, we can also create a cool plot that, do not worry, that's just a rotated by 90 degrees contour of our two-headed streamer. Okay. Also, I would like to show you one more example, and I hope we have enough time for that. Electric cars have nowadays a large range of industrial applications, including cutting, welding, spraying, waste destruction, and surface treatment. Arc discharges are assumed to be under partial to complete local thermodynamic equilibrium conditions. Under these conditions, the plasma can be considered as a conductive fluid mixture and therefore be modeled using the magnetohydrodynamics equations. And the model that I would like to show you demonstrates how to use the arc discharge interface to simulate the discharge generated in an arc, in a DC arc. So let me open another model and briefly demonstrate what's going on there. So that's an approach where we consider our plasma just as a conductive media, so it's governed by laminar flow interface and magnetic and electric fields interface, and we'll also consider the heating, the associated heating. Here we use another library that's equilibrium discharge library, and it contains microscopic properties defined as functions of temperature up to approximately 25,000 kelvins. As you can see initially, that's the conductivity is almost 0. For convergence purposes, instead of 0, we use a small sigma minimum value of 1 Siemens per meter. And moreover, let me remind you that we were aiming to simulate a preheated situation with the some discharge being in place between cathode and anode. So that's justifies specifying the non-zero and non-trivial gradient of temperature. Let me show you, that's just now an increase of temperature close to the axis. So we'll have a preheated channel, and since the temperature is pretty high, we also have now some conductivity that help us to confine discharge. Finally, here that's a stationary simulation where we use a so-called continuation solver to simplify convergence over high current values, and the current is specified as a terminal attached to the top edge of that needle. So results are saved, so we can see that's a pretty warm plasma. We can check velocity distribution, electric conductivity, magnetic flux, and even plot V versus I plot to analyze the arc discharge. And before we move on to your questions, let me briefly summarize my presentation. The electric discharge module, and add-on to the COMSOL Multiphysics simulation software, is used to understand, analyze, and predict behavior of electric discharges in gases, liquids, and solid dielectrics. This includes the analysis of streamer, corona, and dielectric barrier and arc discharges. Applications of the electric discharge module range from consumer electronics to high voltage power system components. With its capabilities for simulating lightning-induced electromagnetic pulses, electrostatic discharges, and other related events, the module serves as an important tool for product development, helping to reduce costs associated with experimental testing and prototyping. The module seamlessly integrates with other products in the COMSOL product suite, including with those for electromagnetic, structural mechanics, and fluid dynamics, enabling users to explore the multi-physics effects often associated with electric discharges. And that concludes my presentation.